We are following breaking news right now in Oregon, just off the Oregon coast. There's been an earthquake. A magnitude 5.5 quake just hit 100 miles west of Coos Bay about 4:30 this morning.
Oregon is hiding something underground. In 2025, USGS models revealed how a Cascadia earthquake could suddenly sink Oregon's coast to catastrophic flooding. By 2026, new gravity measurements at Mount Hood and active uplift near South Sister continue tracking magma shifting beneath the northwest. Today on DiscoverTube, we're following 20 discoveries from the Cascadia megathrust hidden beneath the Pacific to volcanoes, rising ground, sinking coastlines, and new measurements beneath Mount Hood. So here's the question. If scientists can already detect these changes beneath Oregon, what could they discover moving next? 1. The 2025 study that changed Oregon's coastal risk. In May 2025, USGS researchers published a striking new analysis of what could happen to the Pacific Northwest coast during a major Cascadia earthquake. The danger isn't only shaking. During a Great Subduction Zone earthquake, parts of the coast can drop suddenly. Researchers modeled this earthquake-driven subsidence together with rising sea levels. Their conclusion was significant. By 2100, a Cascadia earthquake combined with projected sea level rise could more than triple the area exposed to coastal flooding compared with present-day conditions. That matters especially for low-lying parts of Oregon and Washington. Roads, wetlands, buildings, and infrastructure that currently sit above normal tides could suddenly find themselves much closer to the water. This isn't a hypothetical geological mechanism invented for the model. Evidence of sudden coastal subsidence has been preserved from previous Cascadia earthquakes. The 2025 research simply shows what that same process could mean for the modern coastline. 2. The 700-mile fault hidden offshore. Oregon's largest earthquake source isn't visible from any highway. It lies offshore. The Cascadia Subduction Zone extends roughly 1,100 kilometers, about 680 miles, from Northern California toward Vancouver Island. Here, oceanic plates are being forced beneath North America. Part of that enormous plate boundary can remain locked for centuries. While it's locked, tectonic motion continues. Stress accumulates. Then, during a great earthquake, portions of the boundary can rupture rapidly. The last full margin Cascadia earthquake occurred on January 26, 1700. Geological and historical evidence indicates it generated a tsunami that crossed the Pacific and was recorded in Japan. Oregon, therefore, doesn't need a visible San Andreas-style fault running across the landscape. Its largest tectonic threat begins beneath the ocean floor. And researchers are still improving their picture of exactly what that buried structure looks like. 3. The new 3D map beneath Cascadia. In 2025, USGS researchers released an updated three-dimensional seismic velocity model for the Cascadia region. That may sound technical, but it solves an important problem. Earthquake shaking doesn't move through every type of rock at the same speed. Soft sedimentary basins can amplify shaking. Harder rock can transmit seismic energy differently. So if researchers want realistic simulations of a future Cascadia earthquake, they need an accurate three-dimensional model of what's underground. The 2025 update was designed to improve those simulations and produce better ground motion estimates. Instead of treating Oregon as a flat surface above a simplified fault, scientists can model layers, basins, and geological structures that influence how seismic waves travel. That means future earthquake scenarios can become increasingly local. Not simply, how hard will Oregon shake, but which areas could shake harder because of what's beneath them. 4. The 2025 Evidence of Violent Shaking. Another 2025 USGS-supported study approached Cascadia from a different direction. Researchers examined geological evidence left by previous earthquakes. Their results suggested past Cascadia events may have produced ground accelerations of approximately 0.4 to 0.8 G in some locations. That's strong shaking. The importance isn't the exact number at every site. It's that sediments and geological deposits preserve physical evidence of how violently the region moved during earlier events. Modern Cascadia science therefore combines two approaches. Scientists build sophisticated computer simulations of future earthquakes. Then they compare those models with evidence left behind by actual prehistoric earthquakes. Oregon's earthquake history may be centuries old, but researchers are still extracting new information from it in 2025. 5. The faults scientists mapped in 2026. The Cascadia megathrust isn't necessarily one smooth surface. Near the sea floor, additional structures called splay faults can branch upward from the main plate boundary. These structures matter because they could influence seafloor movement during a major earthquake, and seafloor movement controls tsunami generation. On July 22, 2026, USGS released updated three-dimensional geometries for frontal thrust and splay faults along Cascadia. The dataset was developed for advanced ground motion simulations. That timing is important. Scientists aren't simply relying on maps created decades ago. Parts of the offshore fault architecture are still being refined now. Every improvement changes how researchers can model rupture, shaking, and potentially tsunami behavior. The largest geological system affecting Oregon remains hidden beneath the Pacific, but its geometry is becoming increasingly visible. 6. The strange link to the San Andreas. Then came a surprising study in October 2025. Oregon State University researcher Chris Goldfinger and collaborators examined sediment records from the Cascadia and northern San Andreas systems. Their work suggested that major earthquakes on the two fault systems may sometimes be temporally linked. In other words, the record raised the possibility that ruptures on one system could influence the timing of activity on the other. This doesn't mean every Cascadia earthquake triggers California or vice versa, and it doesn't mean researchers can predict the next event. But the idea challenges the simple view that major West Coast faults always behave independently. Cascadia ends near Northern California. The San Andreas begins nearby. The geological record suggests that, at least during some periods, what happened on one boundary may not have been completely isolated from the other. That makes Oregon part of a much larger Pacific Coast tectonic story. 7. The Oregon volcano that started rising again. Now move inland. About 20 miles west of Bend, the Three Sisters volcanic region contains another measurable change. In 2001, satellite observations revealed that a broad area west of South Sister had been slowly rising. The uplift had apparently begun during the 1990s. Then, the rate changed through time. USGS reports that a new pulse of uplift began around 2020 to 2021. The affected area spans many miles. The movement is measured in centimeters, not meters, but that's exactly why satellite radar matters. A person standing in the landscape would never notice the entire region slowly changing elevation. Scientists can. USGS interprets the deformation as evidence of underground magmatic processes, although uplift by itself does not mean an eruption is approaching. The remarkable part is that Oregon contains a volcanic system whose movement can be measured from space. 8. The 12-mile volcanic cluster. The Three Sisters aren't a single volcano. They're part of a volcanic cluster extending roughly 12 miles, 20 kilometers, along the Cascade Crest. North Sister is the oldest of the three major peaks. Middle Sister is younger. South Sister is younger still. Around them are lava flows, volcanic domes, vents, and other eruptive features. That complex history is one reason the modern uplift west of South Sister attracts attention. Researchers aren't detecting deformation beneath an isolated mountain. They're watching part of an extensive volcanic landscape. USGS combines satellite radar with GPS, seismic monitoring, and geochemical observations to determine whether the deformation changes. The critical question isn't simply whether the ground is rising, it's whether uplift begins accelerating, earthquakes increase, gas chemistry changes, or several signals begin changing together. Right now, Oregon's Cascade volcanoes remain at background levels. 9. The 2026 experiment, beneath Mount Hood. Mount Hood looks permanent from Portland. USGS is measuring it in ways most people never see. In April 2026, the agency released a dataset containing microgravity measurements collected around Mount Hood from 2021 through 2025. A network had been established between Vancouver, Washington, and Mount Hood, and was repeatedly measured over several years. Why measure gravity around a volcano? because tiny changes in underground mass can slightly change the gravitational field. Movement of magma or hydrothermal fluids may therefore produce signals detectable with sensitive instruments. USGS volcanologist Michael Poland authored the 2026 data release. This doesn't mean scientists discovered magma suddenly rising beneath Hood. The network is designed to establish measurements precise enough to recognize meaningful future changes. Scientists are effectively weighing part of Oregon's underground volcanic system over time. 10. The new monitoring station on Mount Hood. The gravity measurements weren't the only recent work. In August 2025, Cascade's Volcano Observatory reported that field crews had installed a new monitoring station at Mount Hood. During that same week, small earthquakes were detected around Hood, but USGS said all data remained consistent with normal background activity. Mount Hood is monitored using a regional seismic network that includes stations close to the volcano. The reason for adding instruments is straightforward. A volcano becomes easier to understand when researchers have years of normal measurements for comparison. If earthquake patterns change, the network sees it. If the ground begins deforming, other instruments can detect it. If hydrothermal or magmatic processes change, researchers have a baseline. Here on DiscoverTube, that's an important distinction. Scientists aren't watching Mount Hood because USGS says it's about to erupt. They're watching because it's an active volcano, and detecting unusual behavior requires knowing what normal behavior looks like first. 11. The volcano close to Oregon's largest city. Mount Hood's location makes it particularly important. The volcano rises east of the Portland metropolitan region and is surrounded by recreation areas, communities, rivers, highways, and infrastructure. USGS considers it an active volcano with significant hazards. One of the major concerns isn't necessarily lava reaching Portland, it's lahars. A lahar is a fast-moving mixture of water, mud, rock, and volcanic debris that can travel far down river valleys. At snow and ice-covered volcanoes, eruptions or slope failures can mobilize enormous amounts of material. That means volcanic risk follows drainage systems rather than perfect circles around the summit. Mount Hood hasn't produced a major modern eruption, but the volcano's location explains why USGS continues expanding monitoring there. When millions of people live within a broader volcanic region, small improvements in detection become valuable. 12. The volcano beneath Oregon's deepest lake. Crater Lake looks peaceful because the eruption that created it happened roughly 7,700 years ago. The eruption of Mount Mazama was enormous enough that the volcano's summit region collapsed, forming the caldera, later filled by Crater Lake. Today, the lake reaches a maximum depth of about 1,949 feet, 594 meters, making it the deepest lake in the United States. But Mount Mazama isn't treated as a permanently extinct system. USGS describes it as a potentially active volcanic center. Researchers studying its history conclude that future eruptions are possible, and unusually, future eruptive activity could occur inside the caldera, potentially beneath the lake itself. The iconic blue water therefore sits inside a volcanic system with an eruptive history that isn't necessarily finished. As of current USGS monitoring, however, Crater Lake remains at normal background activity. 13. The hidden volcano near Bend. South of Bend sits Newberry Volcano. It doesn't resemble Mount Hood because much of Newberry is a huge, broad, shield-shaped volcanic complex. Its summit contains the Newberry caldera with Paulina Lake and East Lake. The volcano has produced lava flows, explosive eruptions, obsidian, pumice, and extensive volcanic deposits. Its footprint is enormous, and its proximity to Bend makes it one of Oregon's most important monitored volcanic systems. USGS Cascade's Volcano Observatory tracks Newberry together with Mount Hood, Mount Jefferson, Three Sisters, and Crater Lake. As of the latest updates, all remain at normal background activity. But Newberry demonstrates why Oregon's volcanic risk can't be understood by staring only at dramatic snow-covered peaks. Some of the state's largest volcanic systems are much broader and less obvious. We've already gone from 2025 Cascadia flooding research and a new 3D underground model to 2026 offshore fault mapping, renewed Three Sisters uplift, and a gravity network quietly measuring Mount Hood. So here's the question: which would would concern you more beneath Oregon? A locked offshore megathrust or a volcanic system beginning to change shape? Tell us below. And if you want more investigations based on what USGS, NASA, NOAA, and university researchers are actually measuring, subscribe to DiscoverTube, because the next Oregon discoveries show that earthquakes and volcanoes aren't the only things capable of reshaping the state. 14. The coast that could drop in minutes. During a large Cascadia rupture, part of Oregon's coastline may experience co-seismic subsidence. That means the land drops during the earthquake itself. The mechanism helps explain strange geological evidence found along the Pacific Northwest coast. Buried soils and drowned forests preserve episodes when land elevation suddenly changed. When the coast drops, salt water can invade areas that were previously above tidal influence. That's why the 2025 USGS coastal flooding study matters. A future earthquake wouldn't necessarily leave Oregon with exactly the same coastline elevation it had before the shaking began. Some communities could emerge from the earthquake physically lower relative to the ocean. Then the tsunami arrives, and decades of future sea level rise could increase the consequences further. The ground itself becomes part of the flood hazard. 15. The shaking hidden beneath Portland. Portland is far inland from the Cascadia Trench. That doesn't mean its geology is simple. Sedimentary basins and local geological structures can influence how earthquake waves behave. This is one reason the 2025 USGS three-dimensional Cascadia model matters. A realistic simulation needs more than the offshore rupture. Researchers also need to know what seismic waves encounter after leaving the fault. Different underground materials can amplify, redirect, or prolong shaking. The result is that two places at similar distances from the earthquake may not necessarily experience identical motion. Modern earthquake science is increasingly moving away from one statewide number toward detailed local models. The question isn't only how large the Cascadia earthquake becomes, it's what the wave encounters beneath your city after it starts. 16. The landslides a Cascadia earthquake could trigger. Oregon's steep western terrain creates another problem. Earthquake shaking can destabilize slopes already weakened by fractures, water, erosion, or previous landslides. A Cascadia earthquake, therefore, wouldn't produce only building damage. It could trigger widespread slope failures. That matters for transportation. Highways through the Coast Range and Cascades often depend on narrow corridors through steep terrain. A landslide doesn't need to destroy an entire bridge to isolate a community. It only needs to block the road leading to it. Oregon researchers and infrastructure planners have spent years examining how Cascadia could affect roads, utilities, electricity, fuel, and other lifelines. Oregon State University's Cascadia Lifelines program exists specifically to help infrastructure providers prepare for these connected failures. The earthquake lasts minutes. Infrastructure disruption could last far longer. 17. The $15 million center studying the next Cascadia earthquake. Recent investment shows how seriously researchers treat the problem. In 2023, the National Science Foundation awarded $15 million to establish Crescent, the Cascadia Region Earthquake Science Center. Led through the University of Oregon with multiple research partners, Crescent became the first U.S. earthquake research center focused specifically on subduction zone hazards. Its work extends well beyond simply locating earthquakes. Researchers study rupture physics, geological structure, tsunami processes, ground motion, and community hazards. That program is part of a larger shift. Cascadia used to be an earthquake source understood largely through geological clues. Now, researchers are building dedicated institutions around it. Combined with the new 2025 seismic model and 2026 offshore fault datasets, Oregon's hidden plate boundary is being investigated at increasingly high resolution. 18. The volcanoes that are quiet right now. This part is important because geological videos often exaggerate monitoring. USGS currently reports that Oregon's major monitored Cascade volcanoes, including Mount Hood, Mount Jefferson, Three Sisters, Newberry, and Crater Lake, are at normal background activity levels. Normal doesn't mean extinct. It means current measurements don't indicate unusual unrest. At Mount Hood, occasional small earthquakes happen. Three Sisters has experienced measurable long-term deformation. Newberry remains an active volcanic system. Crater Lake sits inside the remains of Mount Mazama. Scientists watch all of them because their geological histories show they can produce future activity. But scientists are monitoring a volcano and a volcano is preparing to erupt are two completely different statements. The first is true for Oregon. The second is not supported by current USGS observations. 19. The state sitting between fire and a megathrust. Zoom out and Oregon's geology starts to make sense. Offshore, oceanic crust descends beneath North America at Cascadia. Farther inland, that subduction contributes to magma generation beneath the Cascade volcanic arc. That's why Oregon has both a giant offshore earthquake source and a chain of volcanoes. They're parts of the same plate tectonic system. The consequences appear in completely different ways. On the coast, earthquake shaking, subsidence, and tsunami risk. In the Cascades, magma, hydrothermal systems, volcanic eruptions, and lahars. Between them, cities, highways, rivers, power networks, and communities built across a landscape that looks stationary on human timescales. Oregon isn't hiding one geological mystery, it's sitting above an entire tectonic machine. 20. The instruments watching Oregon change. The biggest change isn't underground, it's how scientists can see underground. Off Oregon's coast, researchers map fault geometry and build increasingly detailed three-dimensional simulations. On land, seismic networks record tiny earthquakes. GPS stations can detect slow deformation. Satellite INSAR can measure changes across entire volcanic regions. At Mount Hood, USGS is now comparing microgravity measurements collected from 2021 through 2025 to look for subtle subsurface changes. At Three Sisters, satellite measurements revealed uplift that would be nearly impossible to recognize by eye. And along Cascadia, geological evidence is being combined with new computer models to estimate how violently future earthquakes could shake Oregon. That's the real recent story. Not that scientists suddenly discovered Oregon is dangerous. Researchers have known about Cascadia and the Cascade volcanoes for decades. What's changing is the resolution. They can see more, model more, measure smaller changes, and connect systems that used to be studied separately. Here on DiscoverTube, that's why Oregon deserves attention. A future Cascadia earthquake could lower sections of coast within minutes. A tsunami could follow. Three Sisters has experienced measurable uplift. Mount Hood is being monitored with instruments sensitive enough to detect tiny changes in gravity. And Crater Lake occupies a volcanic system USGS says could erupt again in the future. Yet Oregon's monitored volcanoes remain at normal background activity today. Those facts aren't contradictory, they're how geology works. A landscape can be quiet right now while still being part of an active system. So here's our final question. What do you think researchers will detect next beneath Oregon? A new Cascadia structure? Another deformation signal beneath the Cascades? Or something completely unexpected? Tell us in the comments. And subscribe to DiscoverTube if you want to follow the next USGS, NASA, or university discovery as the measurements come in. Because Oregon's biggest mystery isn't whether powerful systems exist beneath the state. Scientists already know they do. The mystery is what the next generation of instruments will reveal about them.